All right, well, I guess it's about time to get started. I'm a minute late. This talk may run a little bit over. I won't be offended if people want to get up at the end. Basically, I'm going to go through a bunch of things, and the last thing I'm going to talk about are people's concerns. I put it in quotes because the concerns are really not something you need to be concerned about. So we should get through everything but the concerns in time, and if you're not concerned, then you don't have to worry about it. So we'll go in that order. Anyway, my name is John Lakos. I work at Bloomberg, and my mission in life, it seems, is to convince people that allocators are useful things. And I think that in 2017, I made the rounds, and I think I made a compelling argument that performance alone is enough for people to at least take them seriously. And the purpose of this talk is to ask the very reasonable question, okay, allocators do provide value in many ways, but do they give you enough value to justify the cost of having an allocator-aware infrastructure? Because, make no mistake, there is a cost associated with having everybody be aware of allocators, kind of the same way there is with const, right? If you have some people who use const and some people who don't, it's not very useful. You kind of have to, at some level, say, this library is const correct, because if it's not useful. And allocators are kind of like that. In fact, Matt Ostrin, back many, many years ago, who has a distinct distaste for allocators because of the way they were sort of jammed into C++ 98. And I don't blame him after reading. I was rereading his book to properly reference him in my upcoming book. He makes, I can see why he's a little bitter. But we'll get to that. Here's the copyright notice. Here's the abstract, but you're here, so don't worry about this. This is for the people viewing at home in the privacy of their own house or work. So the current state of affairs, we're going to talk about, local allocators do give you good performance. We know this from Lakos CPP Now 17. We know this from, in fact, a really good talk to look at is the Meeting C++ talk. It's 2 hours, and it provides a really good view of what's going on. So even better than that. Not even CPP. I mean, CPP Now is fine, but I think, as I said, even better is Meeting C++. There are real-world costs, and there are also some collateral benefits. And just because we have performance doesn't mean we should forget about all the other good things that having an allocator-aware software infrastructure give us. And then there are some concerns, also known as FUD. And we want to deal with those because it's not that, people do have concerns, but they need to be addressed. It's not totally unreasonable to have concerns, even if they're not really real. Okay, so what are we going to do today? Present 4 allocator-aware software styles. We're going to separate real from imagined costs, discuss some important collateral benefits of allocator awareness, and address some common concerns surrounding allocator awareness. Advocate for supporting allocator-aware software infrastructure today, and then we're also going to make a business case using a detailed analogy, but then we're going to look at something that might, maybe, address the costs and keep all the benefits. And if we could do that, then this becomes more like a no-brainer. But today we're going to talk about the real cost benefit of what doing stuff is today. So let's do that. So there's the introduction. So dynamic memory allocation is important, right? New delete is usually adequate, but custom allocation is sometimes advantageous, and sometimes it's absolutely necessary. Implementing custom allocation is costly, and so we're motivated now to address the costs of creating custom memory allocation today. And soon, we'd like to find a way where we can do much better. So there are 2 approaches to custom memory allocation. One is just write the data structure yourself every time. Just do it. Okay, we know how to do that. That doesn't scale. That just is. And whenever you do that, there's an associated maintenance burden. And you get the best possible performance because you're doing exactly what you need. And there's a high development and maintenance cost. We know this. And the other possibility is to do a whole lot of work creating a software infrastructure that has allocator awareness built into it. There's a huge cost to that, but the reason we have software infrastructure departments is to factor out the cost of software that is reused so that applications can go faster and be more reliable. That is what software infrastructure does. So yes, there's a cost, but there's a reason for that. It gives you nearly the best possible performance in almost every case. There are some outliers where a full custom data structure will still be the right answer, but they become extremely rare and worthwhile, as opposed to whenever I need some additional performance, my only choice is to go for full custom. Okay, the cost of using allocator-aware components for the application developer is much, 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 much cheaper. There is a cost for creating the infrastructure, but when you're an application developer, the incremental cost of using an allocator-aware infrastructure is almost zero. There's some collateral benefits that we're going to talk about. So here's my airline analogy. And this is really an economics talk. I mean, it's not really a technical, it is, but it isn't. But this is an economics talk because I want people to understand that there is a trade-off and there is price discrimination going on here. We're getting something almost for nothing, and we want to see what we're getting. So imagine an airline, you have first class, best possible service, and you have economy, cheapest possible flight, right? Those are two ends. Now that's the way it was in the beginning, and from a client perspective, this is what you got. Think about it as a plane, right? There's the front, small first class, and there's the rest of the plane, coach. But people are not binary, right? There are people in the middle. There's some need for some variation beyond I'm going to pay $200 for a ticket or I'm going to pay $5,000 for a ticket, right? There's something in between, please. So airlines wisely said, look, there's this curve, there's this utility curve. So if you imagine, if you take the population of people and you sort them with how much they value service on an airline, wider seats, better food, whatever first class means. If you sort the people based on how much they value this, you'll get a curve that looks something like this. Some people really, 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 really value it, and some people don't. The other thing is you have to take into account, some people have infinite money, and the people that have infinite money will go first class because they can. But if you take that off the table, there is a range. Similarly, if you look at it this way, imagine people who are developing software. Some people will value performance or other things more and more and more. Some people could care less, and some people really care about it. That same curve exists. At one end of the spectrum, somebody doesn't care about performance at all. At the other end of the spectrum, I have to have it or I can't do my job. And again, there's a curve. We all agree there's some sort of curve, and this is standing in for that curve. Okay, so now with that analogy in mind, there is this point. Let's call it alpha, okay? So this alpha point below which we're going to go economy. We're going to use what we got. And above which we're going to go first class. We're going to write our own. Does that make sense? Have I said anything that you could possibly argue with so far? Probably not, because I haven't said anything. Okay, now, here we have this cost thing. The cost of writing your own is expensive. See that? That's the cost of writing your own. It's go from 0 to, oh my goodness, right? At some point alpha, you're willing to pay that cost. And that cost is the same pretty much no matter how much benefit you get from it. Once you exceed the threshold where we'd want to write your own, the fact that you really want to write your own or you really, really want to write your own doesn't matter. You've chosen to write your own. Does that make sense? It's a binary function. Okay. So now, this is the potential incremental benefit. The people that didn't write their own get nothing. The people that write their own get the area under the green curve. Do you see what I'm saying? That's the value they get out of spending the money. Okay, so now That is goodness. Green is good. Okay? Now, business class and premium economy, what's that? There are people that are willing to pay a little bit more for a little bit better seat and a free drink. They'll pay a little bit more, like $29. Okay, I'll pay $29. That's fine. I'm not going to pay $5,000, but I'll pay $29. Then there are people that go, I ain't going to pay $5,000. My company's budget is $1,500, or my company's budget is $900. I could pay $900, not $200, $900. Okay, so there's that. So now we have a new grade of service, and we'll call it business class or premium economy. What does that look like? Well, let's say that the point at which someone's willing to spend $29 is here. We'll call it alpha minus. And then there's a point that says, I don't care what you do. I'm going to spend the $5,000 because I need the best. Nothing you give me short of the best will do. And we'll call that alpha plus. And now I've segmented my cabin into 4 sections. So see how it looks now? I have first class, which has gotten smaller. Because, and if you ever look at, by the way, these planes, they're like 6 seats in first class. Then there's business class, which I fly, which, of course, which is much bigger and is much cheaper than first class, but is still more expensive than economy, right? Then there's premium economy, which is much better than economy, and it's only a little more expensive. But thank goodness because I have to fly like 10 hours on the stupid plane and I want to sleep, I actually get a reclining bed, so that's good. I really needed it this time. I don't always. If I'm not sleeping, I can do fine in premium economy. But anyway, so we still have this curve, and now we have a bigger chunk of this curve to benefit from because the cost of premium economy and business class here is the same cost. It's using an allocator-aware infrastructure. That incremental cost is very small compared to not using it. It's not zero, but it's something. So here's premium economy, here's business class, here's the cost. The cost of, if you don't care at all, if you could care less, then there's no incremental cost at all. If you care a little bit, then you start using this allocator aware because you care a little bit. It's like, yeah, it's there, I'll use it. And then, oh, I care a lot. I would have rolled my own. Look at all I'm definitely using it. Come on, for that last 3%, do I really need? No. And then there are those crazy people that are going to spend the money anyway. So now you see we have segmented this into 3, not 2. This is price discrimination, big time. And so now the people that were going to roll their own, they still get all their benefit. They're rolling their own, and there's a cost associated with it. And then the people that didn't have to roll their own still get the benefit because they're getting their utility because essentially everything they wanted they're getting. And then the really cool thing is that there are people that would not have done it. They wouldn't have taken advantage because it was a good idea. I really wanted it, but I didn't have time. I would have had to do 10. I just couldn't do it. But because it was almost for free, they got it. They did it. They chose to do it. And then there are people that still don't care. So this is the model now. This is the model when you have an allocator-aware infrastructure. And so for application developers, it's great because it's like you get almost everything for almost nothing. Who could complain? The trouble is that the companies that do this, they have the infrastructure group that they have to pay for, and the infrastructure group, it's a lot more. It's a lot harder to write this stuff than to not write it. And when I say a lot harder, I'm exaggerating. It's not that much harder, but it's harder. You have to write it, you have to test it, you have to document it. It's more effort for infrastructure people. That's it. But for users, it's not that hard. Look at all the savings we get. This is money saved. This is time saved by application developers. They got the benefit. They didn't need to write their own. If they had enough time to write 2 of their own data structures, now they can write 20 because they'll write 1 that they really needed to, and then the rest, they could get almost all the benefit for all these others. So the utility that they get out of their development time is enormous. Now, I don't think people properly understand, that's why I'm here talking, how huge that is. I think the problem also is that because allocators have been so difficult to use up until now, we haven't really seen the benefit of them, but things are changing. So that's one of the good things. But anyway, so this is the incremental cost savings, and And that's really important. Now, what about this thing here? You see these points here on the curve where the cost function touches the incremental value? So here's something interesting. These are different axes, and those crossing points mean absolutely nothing. Nothing at all, so forget about them. They mean nothing. What we're saying here, what's interesting is that there are these regions. And what we care about is that in this region, you're getting the area under the curve, the utility curve that you didn't get before in the case of the light green. And in the case of the dark green, you were going to get that utility anyway, but you're saving that cost. So you're either getting more utility out of your developers or you're getting less cost out of your developers. Either way you look at it, there's a cost-benefit equation to be considered here. Okay? All right. So, which airline do you think I fly, by the way? Just curious.
United.
Why United? American Airlines, AA. And I use my American Advantage card. And you can consider this an AA meeting. Just want you to have a mnemonic. All right? Okay. So this is another picture. This is one of the pictures in the paper that I'm working on. And just to give you an idea, when it's sort of in shades, when it's not all colored. But all right. Any discussion of this? By the way, this is really the important part of the talk, is the economics of it. And the rest of it, I'll just sort of fly through. As I said, we might go over by a little bit, but I want to make sure you guys understand. Any thoughts? Discussion? Okay. So there could be a bunch of questions, but I haven't thought of them yet, so I'll leave them out for now. We'll go on to the next one. So styles of allocators. Let's talk about the three models. So the first one was the C++11. The second one is PMR, also known as C++17. And then there is the one that I'm going to sort of allude to, but is actually going to be talked about by Alistair and Pablo at CPPCon in, is it really that soon, like 2 weeks? So cool stuff. But what we have today are the C++11 model and the C++17 model. There are four interface styles. There's the C++11 style. There's the BDE, which is our internal one, and C++17 style, which are PMR-based, polymorphic memory resource. And then there's this third one, which is, again, is its own thing. And it, too, internally would be PMR-based. So there are, as I said, there are sort of three models. We're going to talk about them. The pros of the first one, the C++11 one, it is compile time centric. The biggest problem with it, well, the best thing about it is it has absolutely no overhead and it's the most flexible. So you can use it for whatever you want. If you want to use it for shared memory, for anything at all, life is great. The trouble is it affects the type of the object, and you don't have a handle that you can grab onto and pull something out. So if I have, for example, an allocator, and I want to be able to say, what allocator do you use? The C++11 model requires you to be a template. It's ugly. It's not friendly. It's very, very hard to write. And basically, no one will use it. So it was a necessary first step to get people warmed up. The second one, which is moderate cost, is the polymorphic memory resource. In this one, the pros, the great news is you don't have to change the type of the object. Basically, what you're doing is you're passing in a base class, an abstract interface, and that the actual type of the allocator is the derived type. And this works extremely well because it doesn't affect the type of the object. It doesn't invade it. So a vector of my allocator and a vector of your allocator are the same C++ type, and that's a great thing. The cons. It's not zero runtime and spatial overhead, but for all practical purposes, it might as well be. We'll talk about that. The bigger one is that for an infrastructure group, there's significant development right now to plumb the allocators so that when you, for example, if we implement our own container class, we need to make sure that the allocator is propagated to the contained elements, and that requires writing code, that requires figuring out whether the contained element needs an allocator and where it goes and so on and so forth. And so can it be done? Absolutely. Do we do it all the time? Sure. but you need to do it. It's more work. Turns out it's not that much more work, and for most cases, it's pretty routine. But you need to do it. So that's the con. Then the PMR style, the style I just described is one that's been around for 20 years. The PMR style of C++17 is the same model. It just wraps that pointer, that base class pointer, in a class. So it looks a little bit more like C++ looks, where you have an allocator object, but really the object is nothing but a pointer. There's a small syntactic difference. It doesn't really matter. And we expect to adopt the C++17 model because we want to be interoperable with the world, and we want the world to adopt the C++17 polymorphic model by default because we want them to be compatible with us. So I hope that's not asking too much. If everybody could please plan on converting to PMR containers instead of the default ones, if that's not too much to ask, it would be really nice because that will save us some time. When we get to the final model, which we'll talk about, where we're going to relieve you of the responsibility of having to do work, and we'll just do it for you, but that's later. All right, so language support for PMR style allocators. This is something that we're thinking of doing, and we're going to talk about it at CPPCon this year, and we're going to keep talking about it, which is language support for allocator awareness, where instead of you're having to write it as part of library code, you can simply tell the compiler, make this allocator aware, and that's it. So that's it. That'd be nice. More on that later. It means that there would be very little, if any, plumbing. Compiler-generated constructors would be taken care of. All of the syntactic anomalies that happen because you have to write your own stuff would be addressed. So basically, all of the annoyance would be gone. It's a lot like virtual function tables, right? You have a virtual function pointer in your object, and that's it. So what do you care? You said something's virtual, you got a pointer, all right. And it's going to be about like that, because there's a lot of similarity between the runtime type of an object as determined by its virtual pointer and the runtime type of an object as determined by its memory allocator, because both of them are inherent to the object, and once you create an object with its vtab and its allocator, that doesn't change for the life of the object, which is something people may not know, but they need to know. An object never changes its allocator, and it never changes its vtable. Okay. So any AA style that we use is going to have the same performance implications, so it doesn't really matter. So discussion on that? Okay. So I still didn't have any questions. Onward. So the next thing is performance benefits. Well, we talked about performance benefits in the C++, meeting C++ and CPPCon 2017. And in fact, somebody came back in 2018 at ACCU, had seen my talk there, had went to their company and actually started using allocators the way we discussed, and did a little lightning talk saying that they had improved their overall performance by 20% over their entire product line. And so that was their lightning talk, and I was like, nice. Made me feel good. So there really are benefits for performance, and we know it internally at Bloomberg. Paul, you're going to vouch for it, right? Paul's back there. He's a happy client of allocators since what, 2005? Something like that. Anyway, so we have people who are very happy to use memory allocators, and once you start using them, you would be loath to give them up because they really do give you the kind of advantage that you want. So anyway, there are lots of performance gains to be had, and we know that. The question is, which is, is it more important to speed up the allocation and deallocation of memory, or is it more important to allocate memory that's co-located so that it works faster during long periods of time? So which do you think intuitively is the more important one? I mean, they're both important, but one of them has order of magnitude speed differences, whereas the other one has multiplicative factor. Which do you think is the one that's orders of magnitude or order of magnitude? The second one. So locality. If you have a system where memory is allowed to diffuse over your entire virtual memory, and you run the system long enough, has anybody ever seen this, where systems slow down over time? and you have to sort of reboot them, that is memory diffusion. And allocators, local allocators, abate that, they attenuate that because they don't allow the memory to flow outside of their local pools. If you do things right, you can retain the newness, the freshness of the system, and it doesn't sort of degrade over time through diffusion. Do not confuse diffusion with fragmentation. Fragmentation has to do with allocators that are coalescing and all of that kind of stuff, and there's plenty of memory, but it's just not in the right place. Diffusion is something that happens where the memory spreads out over the system, and so when you go to access something repeatedly, the data is spread across many, many, many pages, and you can't fit all of the pages into resident memory, or you can't fit all of the data items into cache. There are two different things having to do with, they're sort of two different levels of this. So we want to take advantage of keeping things close together, and there are all sorts of ways where that manifests. All right, so short-running programs, we want faster allocations. Long-running programs, we want improved memory access. So common usage pattern is to build up a data structure with few or no deletes, access it briefly and tear it down. We use a monotonic allocator for that. That's an allocator that basically allocates very quickly, never gives back any memory, and when you destroy the allocator, everything goes away. If we're repeatedly allocating and deallocating a few distinct size blocks, we have a multi-pool allocator for that. It's perfect for that because it just goes and comes and goes as quickly as you could imagine, and this is a great thing for that if you know that that's going on. If you need to destroy a whole bunch of objects at once, both a monotonic and a memory allocator are managed allocators, so you can create a whole bunch of objects that instead of destroying them individually, you can just pull the plug and make them go away without destroying any of them. And as long as they don't manage another resource, that's no problem. So this is stuff that you can do. And obviously, this is not the first thing you learn when you're working on C++, but when you become a professional and you're doing things in an infrastructure environment and you do want to spend enough time to make it as fast as possible, these are the kinds of things that you can do. And so we would want to do these kinds of things, and we want to package this up so that people could try to use these kinds of things. So anyway, these are a bunch of other things. I mean, caching is one of the issue. Long-running programs, I talked about diffusion. Loss in locality is typically the dominant factor for long-running programs. And local allocators also, as I said, attenuate diffusion. Okay. Local allocators are also awesome for threading, and each distinct thread could have its own allocator. That's certainly one way of doing things. But another way of doing things is saying each subsystem has its own allocator. Now you can have a thread pool, and it doesn't matter what thread is running the functionality, the memory used by the thread is local to the subsystem, not local to the thread. And so that's another way we can get benefits. We can take better advantage of thread pools that way. And we don't have to worry about funny things like destructive interference or fault sharing, because we can ensure that a single thread or a single thing, not this particular thread, but whatever thread is active, is working on this cluster of data, and all of this data will be accessed by only one thread at one time. And so we get that for free. It's one of those, well, we could do it by padding, but padding makes things bigger, and making things bigger means I can fit fewer things in cache and so on. Or we can be smart about it, keep them small, and make sure that the right things are in cache, and that's strictly better. So achieving maximum performance is something that requires global knowledge. It's something that we need to know about. We can't just sort of hope. We have to know how our system is going to work, and then we can do really smart things about our memory allocation. Having this solid understanding of what the different allocator characteristics are is also critical. So quick discussion about that. Anybody want to comment? Okay, questions, more questions, onward. Costs. So to be fair, it doesn't cost users much, but it does cost a lot for an organization to create an allocator-aware software infrastructure. Now we have to start with the standard libraries. We have PMR, so we know that the standard feels it's important. Now the next level up is our low-level corporate libraries? Do we want to make them allocator aware or not? If we don't, then we're kind of telling our clients, well, if you use any of our stuff, it's like saying, well, the library is const correct, but our stuff isn't. So if you use our stuff, it's going to be awkward because our stuff doesn't take allocators, and if you try to mix that with the standard, so now you get this tension, this mismatch, whatever. So in our company, the infrastructure, all of it, is allocator aware. And there are people that, like it and don't like it and this and that, whatever. The people that are complaining the most, of course, are the people that are at that middle level where some of their clients need it, but not really, but maybe, but they were told by management they have to do it because maybe John thinks it's a good idea, and that's where it gets to be tentative. The only reason they're really complaining, number one, it takes time, and number two, their clients get it wrong. When their clients get it wrong, they're the first line of defense, and that's a real cost. People misusing allocators, because like anything else, any power tool, it can happen. So there's an upfront cost of creating this stuff, and the plumbing and all that we talked about that. It's borne mostly by the library and infrastructure developers. The incremental cost of exploiting or ignoring it, that's pretty small, because really the only burden that you have is there's going to be some extra documentation in the function that explains what the extra parameter is and so on. And all you really have to do is ignore it. If you want to use this library and you don't care about allocators, don't worry about it. It's an opt-in kind of thing. So converting an allocator unaware class to AA for typical classes is pretty straightforward. It affects the constructors only. You got to go in and make sure that all your data members are set up. Once you've done that, unless you're a particular kind of class that is like a container or something, you're probably all good. You have to worry about forwarding the arguments and stuff like that, sure. You might denote it as being an allocator-aware thing with a trait. I mean, it's not rocket science. Non-typical classes are more challenging, like containers, for example. And so STD complex, you have to interact with the anus of the element. Okay, that's starting to get interesting. Vector, well, vector we have an append. And when we append something, now we have to worry about a method that's not a constructor, still dealing with allocation. And so that's where it starts to get a little more interesting, and you need to learn a little more about what you need to do to make that work. But again, it's not rocket science yet. And then there are things like pair. And pair is a bear, because pair doesn't care about allocators at all. And yet it has to deal with allocators. So if you're writing a class that it looks and smells like pair or tuple, and you try to do that in C++11, it's really annoying. Fortunately, we have pair and tuple in the standard, and hopefully you don't have to write your own pair or tuple or, God forbid, unordered container. We have Alistair Meredith, who works at Bloomberg, who was testing our implementation of unordered container for a year. The thing is, it's extremely intricate with all of its template policies, and it's a very hard thing to make sure that it works. And we like to get things pretty right, Alistair in particular. So the load factor, like most people would say, okay, if the load factor is somewhere between, I don't know, 1/2 and 4, we're good. But he wants to know what happens when the load factor is like 10 to the minus 9th. And I'm like, what are you doing? But who knows? So anyway, we have to check all of these things, and it's just one of those very expensive things to do. So hopefully you won't have to implement unordered container. Leave that to the standard. So for normal people doing normal things, writing these things is somewhat painful, but it's not the end of the world. Then you get to shared pointer. And shared pointer, you really need to know what you're doing. And I wouldn't even go there. In fact, shared pointer might be something that's outside of the scope of what can be automated, and you might just have some things that have to be handwritten. But this is the true outlier. These things that are not in a class category, that are just their own beast. So maintenance burden. Well, there's more source code, and we know that the amount of source code can range to, let's say, under 20% more, and that source code is boilerplate. So it's the kind of thing that lends itself well to automation, mostly. It's kind of like most things can be done automatically, and we do most things automatically. So that's good. This is a 2017 statistic on our code base, by the way. It requires more training, because we have to teach people how to do this. There's an opportunity cost when Alistair is writing one of these things. He's not writing something else. So if you're writing an allocator-aware, really hard thing, then you're not making money for the company in some other way. So that's a real cost. Opportunity cost exists. Other projects might be delayed. So mitigating factors. It lends itself to automation. We have a tool called BD Verify. We are looking into really automating this with a language feature, which means that you would not have to write this in library code. It would be done for you. And that's an exciting project that we're working on. There is a substantial upfront cost to developing a language feature that makes software allocator aware, needless to say. And if you think about it, the same is true for self-driving cars. And companies like Google are spending, and Uber, they're spending a lot of money for the technology. Why? Because once you have that technology, think about it, other things become much, much cheaper. So there's an upfront cost, but there's a benefit. So the long-term benefit, and we're long-term greedy at Bloomberg. We like things to be cheap in the long run, to be solid and dependable in the long run. And so that's why we invest a lot of money up front to make sure that we'll still be in business 50 years from now. Okay. So anyway, the cost of using allocator-aware software infrastructure is really pretty small. It's much faster and easier than rolling your own. Clearly, if somebody said, here, you have a container, choose your allocator, put the two together, you're done. That's minutes instead of weeks or months if you're doing something reusable. It's easy to supply. It requires additional testing. Okay. If you don't need it, you don't need it. If just go ahead and ignore it and test it the way you always did, because it's purely opt-in. Again, I want to say, if you don't care about this stuff, your biggest chore is ignoring it. Just don't worry about it. Don't think about it. All right. So there's an additional cognitive burden. Users will still see the AA features. There's a larger programming interface. Until we have the language support, there will be that extra parameter. There'll be documentation in English that says optionally supply an allocator used for memory. If no allocator is specified, the currently installed default allocator will be used. There's a boilerplate pair of sentences for every function that you have to ignore. It's in the same place every time. You can just ignore it. Okay. So I've got that there. So the net benefit for people who use allocators, who care, this is a clear win. For people who don't today care about allocators, it's not a clear win, at least not as clear. There's additional opportunity for misuse. If an object were to outlive its allocator, people get scared. They say, well, what happens if my allocator goes out of scope before my object goes out of scope? What's going to happen? And the answer is, well, don't do that. But it's much better than that, because if you create an allocator and then you create an object in the same scope, and you pass the address of the allocator into the object, here's object A, allocator, object B. A was created before B. B will be destroyed before A, done. There's no way around that. The only way you can screw this up is to return the object and have it hold on to some allocator somewhere else. That would be bad. But don't do that. Don't return a dangling pointer. Don't do that, right? I mean, just don't. Anyway, so that's a really rare kind of bug. That's not the kind of bug we're worried about. We're much more concerned that somebody will use the wrong allocator. They'll use a special purpose allocator when they needed a general purpose allocator. I mean, can you imagine? You have an allocator, and this allocator never deletes, ever. It just allocates, because that's really fast. Then you put that in a loop, and you go 1,000,000 times or 1,000,000,000 times. Eventually, you will leak all of your virtual memory, all of your memory that you can use, and you will die. That will happen. So the secret is, don't do that. But you can do that, but don't do that. And so we need to educate people not to do that. So that's an example of misuse of allocators. Now again, there's a million ways, a million? There's a countable infinity, I think, of ways that you can screw up in C++, right? Clearly a countable infinity, right? Because all C++ programs are can put into one-to-one correspondence with the integers. Right, Andre? There we go. So therefore, there are a lot of them. And this is just another way to screw up. But that doesn't mean we should disenfranchise people who actually care about what they do and want to make things run like nobody's business. So anyway, if you misuse the thing, either it can be a disaster or it can just be waste of your time, but it's still costly. So it's incompatible with some modern C++ features. Trivial constructors, no good. You got to write everything yourself. So you can't rely on compiler-generated stuff, and that's really unfortunate. And there are other things that don't work really well, like aggregate initialization. And so all of these things are annoyances that get in the way. And then just imagine if we had language support that took all of that off the table and said, no, it's all good. It's just like virtual functions. It's all covered. We got it all taken care of. Well, if we had it all taken care of, then this would be a different conversation. But we don't have it all taken care of yet. So not there. Anyway, there's also the assertion that allocators somehow get in the way of writing modern interfaces or doing something with moves or whatever. And that is false. And it's so infuriatingly false that I had to save it for later so I can actually let my hair down and what hair? And rant and rave about it, but I don't want to get into it now because I'll lose my composure. So I'm going to stay focused. Okay, lifetime management issues. Okay, the productive lifetime of an object must not exceed that of its allocator and requires additional care, all of that good stuff. Certain standard facilities limits what they can do. So shared pointer and weak pointer, you have to pay more attention to what you're doing if you're dealing with allocators. You can't just go, whatever. If you start to use allocators with shared pointer, then you have to pay attention. That's okay. You do have to pay attention, but if you do it, or you could say, you know what, I don't want to learn that today. Next year I'm going to learn about allocators and shared pointers. I'm not going to do that now. Okay, so that's fine. So it requires education, tools, governance, administration. People have to be trained. There have to be code reviews by people who have been trained to do code reviews. There need to be development-facing static analysis tools. We have that. Company-wide policies on when and when not to use allocators. It's not atypical of other powerful paradigms like multi-threading, unit testing, and C++ itself. When do you use multiple inheritance? Is it never? No. It's don't use it unless you have a good reason to use it, then use it, just like anything else. Don't use it just because it's there. Use it for a reason. We have templates. Oh, everything has to be a template. No, it doesn't. Be calm. All right, bottom line. So real substantial costs exist. Substantial upfront library development cost, modest incremental application developer costs. It's a credible value proposition, though. It's at least there's something to discuss here. And if we don't have a hierarchically reusable allocator-aware software infrastructure, then some applications will roll their own. They will not be reusable in any way. They will incur a maintenance burden for the application developers. When the application developers leave, somebody else will inherit that maintenance burden, and life will go on as is typical in many companies. Everybody else who can't afford to write that will have to do without, and we will lose the area under the curve for all those people that wanted it but couldn't afford, didn't have time to write it themselves. Discussion. So I covered the costs, right? There are costs. There are benefits, there are costs. Well, there are more. There are a lot of questions, but I don't know what they are. Okay. What is the percent of code that benefits from allocators? Somebody asked that one. So, do we know? I don't know. It really depends. If allocators were really free, I would suspect that a large amount of code would benefit a little bit if they were really free. If they're the way they are right now, I would suspect a percentage. Is it 10%? Maybe no. Maybe it's 5%. Maybe it's 3%. But I'll tell you this, the 3% that benefits, oh my goodness. The 3% that benefits will save you, millions of dollars, billions of dollars in compute cost or in heat dissipation or whatever. It's those cases where you need it that drive the business. The rest of the stuff is glue logic. Who cares? But those really things like evaluating a portfolio in a brokerage house where you've got to go through this loop of horizon and scenario and da-da-da-da-da-da-da, and you're trying to do things as fast as possible. Those are the places where performance really matters. And if you're trying to do some, high-performance, multi-threaded system, those are the places where it matters. So it's not really the percentage of code. But anyway, there's a question somebody asked. If anybody thinks of another question, please let me know. All right, so there are collateral benefits. The collateral benefits, not just performance, but apart from performance, there's also rapid prototyping, modularity, hierarchical reuse testing, instrumentation, and object placement. So these are all things that you get with this infrastructure for free, along with the performance. So you have the ability to tune for performance, and monitor, and measure, and place, do all kinds of good things. You wouldn't get the rapid prototyping in the one-off. In other words, in some ways, it's kind of like in business class, by the way, I don't know if you know this, but first class is actually up near the pilot. There's no door there. So in the event of an emergency, the first class passengers have to walk past the business class passengers to get off the plane. Whereas the business class passengers sit right next to the exit. The exit is right there. And so you can think of, in some ways, business class has it a little better because they're faster. So if, unlike a full custom solution that might take months to develop, I can try my business class solution right now, and it might be good enough. Or it might not help at all. And if it doesn't help at all, I just saved myself a whole bunch of time. But if it helps enough, I'm done. And if it doesn't help enough, but it helps a lot, I can make my clients happier today, knowing that I have 2 months from now a full custom solution on the way that's a bit better. But at least you got something now today that's 80% of the way or 60% of the way. So there's that. So there are some advantages to this, and performance being one of them. Those are collateral benefits. It's low cost, low risk, so that's wonderful. You've got these plug-in components. You can measure, tune. You can repeat as needed. You can deploy immediately. So again, this is this whole thing, as I just said, you go through this cycle where you try it first, and if it looks good, you ship it now, and then you ship it again later, and if it looks bad, you try something else, and you don't waste the months of development. So rapid prototyping is a benefit that you get that you don't get with the other. I just want to be clear. You get that for free. All right. They're chainable. One of the things that's nice is, Andres talked about trees of allocators and whatever. I'm simple. I like the linear thing because I can handle that. And so being able to chain together something that allocates little things, that falls back to something that does big things, possibly to something that measures things, you can chain them together and you get this composition. It's simple, but for my purposes, it gets my job done. So I'm really happy, and it's easy to explain and whatever. So these kinds of allocators are good. I don't think it's impossible to have more elaborate allocators, but it's not part of what I'm selling. It would be something on top of what I'm selling, and certainly doable. There are other things that can be done. Small block allocators falls back on a large one, as I said. Memory is needed. Suppose one allocator supplies some feature, metrics. This is something that we actually do. There's a great example where one of them is test allocator, where we start to measure things. How much memory is used by this object? Now, there are tools that you can use to measure the amount of memory used by a type, or the amount of memory used in this region, or whatever. But when it comes down to object systems, and you want to say, I have 10 systems that are headed by my system object, and there are 10 of them. I want to know how much is system, the object named system 1, how much memory is it using? How much is system memory 2 using? There are tools to do that in the same way that there are tools to look at regions of code. So what's nice about these kinds of things is the test allocator checks for leaking memory. It can log allocate calls. It can match allocations with deallocations. It can be used for testing exception safety in the classical way. We can do memory range overwrites with sentinels. It's non-invasive, And what's really cool is it scales arbitrarily large, and it can coexist in running production systems. And this is stuff that really happens. So there's this wonderful thing that someone developed at Bloomberg. His name is Brock Peabody, and it's something that's used today in data layer. And it's awesome because what you can do is you can, using the allocator interface that's ubiquitous, you can have an object that is both an allocator and a monitor. And so this interface, this thing here, also has another interface over here that you can't see that's called monitor or some such thing. And there's an object that is both an allocator and a monitor. And for those subsystems that want to participate, they can do a runtime dynamic cast and say, do you participate in monitoring? And if the answer is yes, it can give the information to the monitor. So we're using this vehicle, this Trojan horse, if you will, to allow us to monitor willing subsystems. It's an opt-in thing, but it's something that's been done and it's used in production, and you could not do it without having an allocator-aware software infrastructure. So anyway, I said all that. Now I'm going to put it out on the slide because that's what the slide is for, but I got ahead of myself. So there it is on the slide what I just said. All right. So we can put objects in memory. We have placement, new and delete. Those are wonderful things, but they're not good enough if you want to put the whole object in memory in one place. What if I have a memory mapped I/O device and I want to put my whole vector of strings, all of it, in this thing and then put it out on disk and then bring it back and then use it? We do this. We do this at Bloomberg. And we can do it because we can place the entire object in an arena. You can't do that with placement new. So that's just another thing that doesn't happen. So I said all that again. I'm getting ahead of myself. This is what Bloomberg does. So gmalloc is the function that does exactly that. We have I/O mapped memory. All right. There's another interesting thing. We can use allocators for something that's not just performance or monitoring. We can actually architecturally use allocators. We can say that I'm going to create this graph. And if you think about how expensive it would be to create a graph of shared pointers and have each one worry about itself and what happens if you have a cycle and whatever. Or you can forget about that. You can create your data structure with plain old raw pointers, which is not the end of the world. And then at the end of the day, when you're done with it, instead of having to go around and destroy all of these objects, you can just simply release all of that memory. And you don't have to worry about cycles or ownership or anything because you say, I'm done with the graph, and you pull the plug, and that is your garbage collector. It's all collected, and it is absolutely faster than anything you could possibly do the old-fashioned way using modern C++. Okay. So anyway, again, that's what I just said. I just told you what's on this slide. It's an interesting lecturing style, right? First tell you what I'm going to say, then put it on the slide so you can read it, and then I think I'm just tired. Sorry. Okay. So it's an open-ended value proposition. There's so much you can do with an allocator-aware software infrastructure that makes sense, that gives the firm advantages that there's it's hard to not appreciate that there is a value proposition to be had. But anyway, so I'll put this up, and the idea is we just to have these benefits without the without planning for it. Sort of, it's like you do it wholesale. You either do it for everybody, or it's rare and it happens occasionally and it's not a thing. Or you make it available. It's like healthcare for all in some sense. I guess I'm not supposed to use that because that's a contentious thing. You know, do we want public healthcare? Anyway. All right. So there's concerns. Does anybody have, we have 5 minutes left. This is the part that I was trying to get to so that people said, okay, I believe you, I don't need to hear anymore. But it's true, allocators have not been treated well in the past, and people have a bad taste in their mouths. And C++ 98 was useless, and C++ 03 was all but useless, and C++ 11 is not much better, and C++ 17 is much better, but still people have a bad taste in their mouths, and I understand that. And a lot of people who are otherwise very gung-ho on performance and being able to do articulate things will tell you, we don't need allocators. I don't know what to do with that. Not everybody needs allocators, but the people that need allocators need allocators. And so people invent reasons for not liking them. And here are some of the reasons that people invent. These are invented reasons. State-of-the-art allocators, global allocators, are as good or better. Now, I'll replace my global new and delete with a better allocator. Yeah, that'll solve it. Like, why didn't we already do that? What's wrong with you? Do that. Now that you've done that, now let's do the same exercise again, because now our starting point is the best global allocator you have. And our starting point from there is, now let's make it 4 times or an order of magnitude faster than whatever that starting point is. So that argument doesn't exist. And we know because we did the measurements. We know that the best allocators that can be are there. We can't do better than those. And now we can do either a factor of 4 or a factor of 10 or a factor of 16 better by doing what we do. So that's not even a question. The next one is the PMR violates zero overhead principle. Another one is generally poor runtime performance trade-off, meaning that, well, if everybody has an allocator pointer, then the thing will run slower in general, and that's a bad idea. Nonsense. Absolute nonsense. All right. It's an unmanageable amount of verification and testing complexity. Again, if you believe that, then don't use it. Understood, you're not there. But if you are there, don't disenfranchise those people who are there who need it because you're not there. Gross incompatibility with modern C++ style. This is absolutely false. There is nothing about allocators, nothing I tell you that in any way discourages modern C++ style. There are other things that discourage modern C++ style, but they aren't allocators. Just want to be clear. If you take allocators off the table, there are things that discourage modern C++ style when it comes to performance. We'll get to that. They don't play nice with modern C++ move semantics. Again, nonsense. And that's just a myth that is being propagated, and there's zero truth to that. And object pools and factories are as good or better. And again, this is something that people say because it feels good, but it makes absolutely no sense when you think about it. So if you think that all of these things here are FUD, and you know for a fact that there's no truth to them, then there's nothing else to hear, because all I'm going to do is go through them one by one and tell you why they're not true. So that's the rest of the talk pretty much. So I'm just saying, if anybody feels like they are done for today, I can understand that. But I'm probably going to go for another 5 or 6 or 7 or 8 minutes. Okay, well, here I go. So state-of-the-art global allocators. I'll say it quickly. Here it is on the screen. This is the concern. Advances in global memory allocators have led to dynamic performance improvements, especially with respect to real-world multi-threading applications. Would replacing the compiler-supplied global memory allocator with a newer state-of-the-art one achieve most, if not all, of the real benefits derived from assiduous use of local allocators designed into a program? Okay, no. No. General-purpose global allocators are ignorant of application-specific details. They cannot achieve the locality that local allocation can. One of the things they benefit from is knowing which thread is doing what and thread local pools. But if you design your system so that you have thread pools, then the affinity isn't there, and there's nothing the global allocator can do to recover from that. So the local allocator builds into the design what it is that's local, and it keeps it there. And so that's how that works, period. And that's how you avoid the fault sharing. That's how you avoid those kinds of things. They don't provide the collateral benefits in any event. No matter what you say, you can't go on an object-by-object basis and place it or measure it or do anything with it, right? That doesn't exist. And they certainly don't do anything for rapid prototyping. So if you just stop, that's not a panacea for anything. Okay, zero overhead principle. So everyone but the C++ 11 allocator model, you have to store a pointer somewhere in your object to the allocator. You don't have to store it in the footprint, but we choose to store it in the footprint because after measurement, storing it anywhere else, like in the allocated memory, which we could do. And by the way, people go, wait a minute, vector has 3 pointers. If we add allocators, it's going to have 4 pointers. Again, a myth. A vector does not have 3 pointers. A vector could have 2 pointers. A vector could, on some platforms, have 1 pointer. Or a vector could have size of 16 pointers because of the short vector optimization. It's all about whatever your usage pattern says is best. Our experience is that having the allocator in the footprint is faster than not because we've measured all of them, but that's a measurement that could change. The point is that it is an implementation choice to use the fastest way. But I will tell you, if you're worried about space, storing the allocator pointer only once you've allocated memory is a viable option. And at that point, once you've allocated memory, the memory that you've allocated, having the pointer with that memory, is exponentially, literally with geometric growth, exponentially negligible. So it's one of those things that you could even measure the cost, because we've tried. There is no cost. So any conjecture that there's cost is without any experimental evidence. Okay. So I'm just saying basically that the zero overhead principle is not in spirit violated by having allocators in the polymorphic sense. The virtual function dispatch is also a myth. That's a wonderful one. For the most important case, where you have an allocator created on the program stack, and then you have a data structure, and you pass the address of the allocator into the data structure, the allocator's virtual function will be inline. And the compiler will see that inline function along with the template that it's going into, typically a vector or whatever, and can de-virtualize it with no effort whatsoever so that the code looks just as if it had been invasive. So it has all of those wonderful properties of performance that you want for the stack allocators. For every other notion of allocation, it is completely meaningless because the true benefit comes from the locality that you get and not from the cost of allocation and deallocation. I cannot say this more strongly. There is no cost. There's no cost that we need to worry about when it comes to that. What we're getting, the benefit, is enormous. Think of it this way. If you don't care about performance, don't worry about allocators. The overhead will be not measurable. If you do care about performance, the overhead is irrelevant compared to the tremendous gains that you'll achieve. And so the net benefit is like, I'm spending a penny and I'm getting $1 million. What is the discussion? So that's where that is. The next one, zero overhead principle is almost unfair. We're making design trade-offs. One design trade-off we do is we take things that there's a negligible cost to everybody, but we really improve performance, on average. That's one. Another one is there's a solid benefit for a few, but there's a slight cost to everybody. And then there's one that's a large benefit for some people, or there's a benefit for some people, but a significant cost for others. The third case is the one that we try to stay away from. You never want to make a change from an existing system where before people were happy, and then there are some people that are unhappy. And I'm saying that the kind of change that allocators would do, no one would become unhappy because no one would notice anything. There would be no change for them. But for the people that would notice a change, the change would be huge. So of these 3 trade-offs, we don't do 3. It's a combination of 1 and 2. That's the kind of trade-off that having an allocator-aware infrastructure gives you. That's my argument. It's like the allocator tax. Everyone must buy auto insurance. Everyone. Accidents are unusual, but not rare. So if everybody is paying for auto insurance, and you happen to be one of those unfortunate people that need an allocator, you got one. It's an insurance policy. Okay, so verification and testing. This basically, failure to properly annotate types or propagate allocators can undermine the effectiveness of the allocation strategy and can lead to memory leaks, especially when winking out memory, which is one of the things you can do. Aren't the extensive verification testing and peer review required to avoid such errors impracticable? One of my great words. Can we not put it into practice? I think we can. It does require effort. It requires people who are going to use this to be smart. Almost every new library feature will need some training. Yes, there are special purpose allocators that you shouldn't use, and winking out is clearly for experts only. By experts only, I mean somebody who has actually listened to the talk, has actually went to the lecture and go, oh, I understand what that's for, instead of just going, let me try this thing, and cluelessly puts two things together and has no idea whether they even belong together. That's the kind of thing that's just nuts. The test allocator is a great thing, and if we had this 20V thing, that would be awesome as well. So compatibility with modern C++ style, I have to read this. C++11 encourages a style of programming where objects are more often passed and returned by values, sometimes relying on R value references to move these objects efficiently, whereas BDE style relies on passing A objects by address as arguments to achieve optimal efficiency and control over the allocator employed. Isn't this old-fashioned style unjustifiably restrictive? So one of the crazy things about this is it has nothing to do with allocators whatsoever. Returning by value is inherently inefficient, whether you have control over the allocator or not. And that is because the returned object must be constructed in order to return it. And once it's returned, it must be destroyed. It cannot be pooled. Because it cannot be pooled, it is a bad idea, period. If it could be pooled, then we could reuse the object. Then it wouldn't matter how we got it, and the way you do that is to pass it in as an argument. Let me not belabor that. Supplying an allocator doesn't help. The idea that you would supply an allocator on that function line doesn't matter. What you need to do is create the object with what allocator you want, whatever that is, pass it in and reuse the object, and you could get it from a pool, you could get it from wherever you want, but you need to pass it in. Okay, returning an object by argument is just straight up faster, and you can reuse the object. I already talked about that. This is the accumulate pattern I learned from my last talk, and you have full control over the allocator if you want it, but even if you don't, it's still faster. You can build on the return style. If you really want to have an object returned by value, you can. You can build that on top of, as a layer on top of these other things. You can't go the other way around. So this is just the way it has to be done. When two objects use different allocators, move assignment degenerates to copy operation and swap becomes undefined. Doesn't this imply that local allocators should be avoided to enable such operations? So here's the crazy thing. If you're going across a memory pool and doing so would cause a huge degradation in performance, you could either hide your head in the sand and let that degradation occur, or you could just admit that a copy is faster. And if you just admit that, then you've got a good design. By not allowing allocators, you're just basically not looking at the data. And so that's a ridiculous argument. Move versus allocate. Move assignment is often not as efficient as copy. And again, this is the crazy thing. Copying is often faster when the cost of moving results in diffusion across your region. So it really depends on what's going on. Clearly, if you're inside one object, moving is not as bad. There are details that we can get into. But moves have nothing to do with return by value. All of that is handled by RVO and NRVO, and all moving does is muck around with the memory. There are four aspects. I'll put them out here now. Locality is the big one. Construction or constructive interference or true sharing is what I'm saying is another good one that you get from having these local allocators. Prefetching and optimal n-way cache. Memory bank access is another, and if you do moves within the same memory pool, it's not so bad. Like if you want to shift the elements up in a vector, okay, do a move because you know that's going to be the same allocator. That will preserve 1 and 2. It may not preserve 3 and 4, and that may be okay. But if you're writing code where you really care about the particular cache of your system, like the size and the way it's, I think then you need to become more of an electrical engineer and not a computer programmer, and then that's fine. But you should be aware of it. In other words, you should be aware of these things. So object pools and factories serve to reduce overhead caused by allocating memory. So why aren't these approaches as good, if not better, alternatives to allocators? So the crazy thing is that memory allocation is needed by object pools. You have to create the pools in the first place, and it's like, do moving vans eliminate the need for furniture companies? No. Object pools are a higher level abstraction. We absolutely want object pools. We want to implement them in terms of allocators. We want to gain the benefits of all the benefits of allocator-aware architecture from them. And so, that's basically what this slide is. You have memory allocators, memory pools, object pools, and there's a hierarchy, and you use it at whatever level makes sense to you. If you're an application developer, an object pool might be the right answer, but you build the object pool out of the memory pool, and the memory pool is allocator aware, and the object pool should be allocator aware, and then it can enjoy all of those benefits. And that's what I'm about to say here. Discussion. All right, questions. So anyway, just to wrap up, allocator aware software, performance instrumentation, object placement, these are all good things. Historically, we've had to write bespoke data structures, and they don't give us these values, these benefits. Allocator aware software structure has real costs, and here are some of the examples. There's resistance based on how badly we did with C++11, and I'm sorry about that, but it was just one of those necessary things. It's not that we didn't know, it's that we couldn't convince the standards committee to take the big step to go to polymorphic because they were scared to death of virtual functions. Really the truth. So there are all of these wonderful benefits. We talked about, there's the costs, there's the collateral benefits, there's some FUD, and do the benefits outweigh the costs? And then finally, suppose we actually could remove all the costs, all of the annoyance associated with allocator-aware software infrastructure so that you got it for free. There was no allocator parameter, there's no extra documentation, there's nothing. It literally is the same as saying virtual. Like just say AA, done, and that's all you had to do. And if that were all you had to do, and then when you came to a class and you say inject this, you don't even pass it in as part of the constructor. It's not even part of that. If you could do all of that, then what would you say? Should we invest in this? Because if you think about self-driving cars, if you have a self-driving car, the cost of making, if you have the technology, the cost of having a self-driving car versus a regular car, they cost the same because the only difference is the software and a few sensors. So it's really the same price. It's the upfront cost that's amortized over the rest of all humanity. So we think it's worth it, so we're doing it. We're the Uber, if you will, because we use allocators and we want to save the benefit, the cost ourselves. So we're going to go ahead and do this. We are doing this, and this is what this is our contribution, and it's going to be a hard sell because people still aren't convinced of the cost-benefit trade-off. But it's really hard for me to imagine that if there were no cost, that you'd really have a problem with this. And that is the end of the talk, and thank you for staying a little late. I'm sorry I did it as fast as I could.